Sera intanto, poi I will do we have non-Italian speaking guests. I am really happy and proud to introduce our guest for today. Last time that I introduced Elisabetta was during Madeline's lecture at the EGU last year. Elisabetta Erba is, for those of you that have never met her, she's a full professor of paleontology at the University of Milan, and she is a world-known expert on calcareous nanofossils. But I mean, the word micropaleontologist would not completely describe what is the research of Elisabetta. She's a stratigrapher. I would say that the first word that I would use to describe her research is that she's a stratigrapher, the kind of person that you all need when you want to know the age of a rock. That is always the first thing that you should know about the rock. So she's a stratigrapher, and she's an expert of a particular group of microfossils that are very important for biostratigraphy of the Mesozoic, that are the calcareous nanofossils. Well-known expert means that if you say Mesozoic nanofossils, people will say Elisabetta Erba. So this is the kind of primacy that she had in her field. But with nanofossils, Elisabetta, well, she uses them to date rocks, and this is already important. But what she's really interested in is to look at the response of nanofossils to the global perturbation of the ocean and of life. This is a main topic of research. On this topic, she has been active since the beginning of her career, even if her first paper was a Nature paper. That is a good start always. So she started with a Nature paper, and that paper was on the Pliocene, so in the Pliocene anoxic sediment of the Eastern Mediterranean. But she started with Nature. It's always a good start. And then she moved to nanofossils, and she has been working on this topic for all her career. She has been and she still is a kind of guide for all the Italian international community working on paleoclimate, on CO2 triggered climate change. And well, she has produced more than 150 papers with more than 10,000 citations. Her top cited papers, 5 papers get 2,000 citations. That is the total number of my citations. Yeah, I mean, my production is totally different. And so we are really happy to have Elisabetta here. And the topic of her distinguished lecture today is nanofossils and the response of nanofossils to perturbation during the Mesozoic. Please, Elisabetta.
Thank you, Mariano, for the very nice introduction. And I'm also very happy and honored to be here. And I have a number of friends who live here. None in micropaleontology, actually, but vertebrate paleontology, petrology, segmentology, stratigraphy. And that's a good sign, because it means that earth sciences is really, or geosciences is really multidisciplinary. So we can start. And why talk about the Mesozoic ocean? Because if you look at our planet, the ocean is by far the oldest and the largest ecosystem of Earth. It hosted the most abundant and most diversified biosphere. And it's amazing that, if you look at the pelagic realm, which is almost entirely the oceanic ecosystem, if you go a little bit far away from the coastlines, all this amazing variety of organisms, from the tiny zooplanktonic forms to the gigantic fish and marine animals, they all rely on this creature here, phytoplankton. And in the modern ocean, there are essentially 4 major groups of phytoplanktonic organisms. And Donato, you will forgive me for the oversimplification, but just to be informative at the basic stage. So they are cyanobacteria, diatoms, xenoflagellates, and coccolithophores. And altogether, they are the primary producers, which means that they are the food for the rest of the trophic chain. As we can see in this figure, which is the concentration of chlorophyll, because they produce chlorophyll, their distribution, so the amount of organic matter is not even in the ocean, in surface waters. So we have the highest productivity and the highest availability of food in the permanent Aquarian region at the equator along the continental margin at high latitudes. But even where we have these dark blue spots with very low chlorophyll concentration, still we have hundreds of thousands to million cells of these primary producers. And coccolithophores are a little bit special because, of course, they do photosynthesis as all the other primary producers. So they convert or they absorb the CO2 to produce the organic matter and oxygen as a waste product, but they also must calcify. And therefore, they use some other CO2 taken from the atmosphere in the form of the carbonate ion, and in combination with calcium ions, so they produce calcite and produce some other CO2 that goes back to the system. Next. So this is part of what is called the forest of the ocean. And coccolithogenesis, the biopacification process, is an intracellular process. So this tiny organism, just a few microns in diameter, they produce species-specific tiny calcite crystals. They build together like the Lego bricks, these individual coccoliths. And once they're ready, they're pushed out of the cell to cover entirely the membrane and build what we call a coccosphere. So a coccolith is one of these things, and the coccosphere is the shield along the cell. The next. And so coccolithophores are very important for the carbon cycle, both at the short, medium, long term, and both in the organic carbon and inorganic carbon cycle. And arguably, the production of calcite is a most effective way to take out some CO2 and store it on the seafloor or in the deep ocean. So arguably, the modern ocean, as we know it today, started when this specific group of phytoplankton learned, by chance or by necessity, those to calcify. And this happened in the Triassic. And since then, let's say 240 million years ago, they continue to produce coccoliths and coccosphere one after the other. And so they produced this ability to build very different types of coccolith and coccosphere. Just a few examples of living coccolithophores. At the moment, there are about 300 species in the oceans. So these are some of the living forms. Of course, they are computer painted because they are made of low magnesium calcite. They're white in color. And I think you can appreciate the variety of crystallization of ultrastructure of the individual coccolith and coccosphere. Okay. And this process is going on since Triassic time. Every species has a coccolithogenesis rate, which is slightly different. It can go from minutes to a few hours to build one individual coccolith, and the reproduction rate is on average of 1 or 2 weeks. But in some cases, especially at high latitude, under a specific combination of temperature and nutrients, they can be so abundant, like in this case, Emiliana axley, the most abundant and most recent coccolithophore species, to produce what are called white tides, or these whitish or very light green or very light blue spots. And because of this, the reason for this is because they can be as abundant as billions of cells, so of coccospheres, in 1 liter of water. And so they turn the surface water into a kind of milky appearance. So these patterns, if you go to the next one, other examples, and so this depends on the concentration of calcite, and these designs are due to the surface currents. They stay for maybe 2, 3, 4 weeks, and then they vanish back to normal reproduction rate. So even where you see this very dark blue, you still have probably millions of copolyps. The next. So different species, they produce different rates of copolyp, but it's an ongoing process since hundreds of millions of years. And they live in all the surface waters, different species, different abundances, from the equator to the polar regions, from the coastline down into the open oceans. Okay, so you can find the copolyp everywhere. And in the next one, so their ability to build these calcitic plates and topospheres arguably make this group a most effective producer of calcite on Earth, despite the very tiny size. And what happens after they die, every week or so, they start to fall down across the water column, and I like to think about a summer rain snowfall. So you should imagine these flakes, white flakes, going down very slowly to the seafloor. And if the seafloor is shallower than the calcite compensation depth, you make this type of sediments on the seafloor, essentially everywhere in the oceans. So just a few examples, like snow on glaciers. So you have these white sediments in the pelagic environment. So they are nanofossil. So nanofossil is the word for the fossil form that can be reached down to 4,000 meters. This was the same back in Mesozoic times. So these are the few copolypores of Jurassic and Cretaceous time. So of course, different species, but the same process of copolypogenesis and sedimentation. Next. And so they have a very long evolutionary history. They developed very rapidly. There were a number of biomineralization innovations in terms of crystallography, and they reached the highest diversity in the late Cretaceous. So we have hundreds of outcrops everywhere in the world. They are marine in origin, like the White Cliff of Dover here in South England. This is a copolyp numberlith sediment dated back to 90, 80 million years. So if you take a piece, just like a lot of copolyp, okay, you have also some forams, some radiolarians, but essentially copolypores. So next. So we also have hundreds, of course, that are drilled and recovered from all the oceans at very different latitudes. The oldest site was drilled in northwestern Pacific and reached basalts of the Middle Jurassic time. So we can go back in the ocean today to approximately 160 million years. And in many cases, we have this nanofossil limestone to use to reconstruct ages and many other things. So they are studied since the late 70s of the last century, not because they are difficult to be studied, but because you need to have a high magnification microscope with very high magnification. And so it was immediately clear that they were and are extremely important for dating rocks, as Mariano said, because they are extremely abundant. They have a very large taxonomic diversity, rapid evolution, and a high preservation potential. So if you look at the Mesozoic history of Calcareous zooplankton, essentially all the orders were already placed during the Mesozoic. But it was also clear very soon that in addition to dating, they were extremely useful to understand the sedimentation because they were widespread everywhere and already reached rock forming abundance. So really formed sediments and rocks. And so I think about cocolithogenesis as Polaroid cameras. So I imagine every single coccolith or cocosphere as a snapshot that we're capturing the characteristics of the oceans in that moment in terms of temperature, chemistry, fertility, and so on. And so we can understand how the ocean has been working, and I will try in the next part of my talk to provide you with data and interpretation of good times and bad times for Mesozoic cocolithophores, and try to understand what a normal ocean was, in addition to the major perturbation or some major perturbation that affected the entire oceanic ecosystem. Why? Because we all know that our planet is affected or is experiencing a number of global changes, excess CO2, global warming, droughts, but also extreme floods, and so on, heat waves. So we are maybe reaching a tipping point and perhaps soon enter a state which is essentially unknown to our experience, at least in the last centuries and so on. So, next. Okay, if we look at the oceans, some of the parameters which are really changing the ecosystem is global warming. And you have to think that this 1.5, almost 2 degrees Celsius increase that we have already reached, 97% of the heat is stored in the oceans. So the oceans have been warming up a lot, much more than the continent. The next. The same is true for atmospheric CO2, the famous killing curve. So we know that there has been a 50% increase since pre-industrial times. And even with instruments, it is proved that parallel to the increase in CO2 in the atmosphere, there is an increase of CO2 in surface water, and this means a decrease of pH. The next, and why? Because CO2 is absorbed in surface water, plus water makes carbonic acid, which splits into bicarbonate ion and hydrogen. The more CO2 in the atmosphere, the more hydrogen is released, and this lowers down the pH. And ocean acidification is already in place. And it's quite possible that before the end of the century, pH will lower further, maybe of another 0.2, 0.3, 0.4, which is really a lot. And why this is scary? Of course, for carbonic chemistry, especially for the calcifying marine organisms, and of course, for polyphenols. So, how can we assess the ecosystem resilience relative to global changes? First of all, what is resilience? We heard this word every day. We have the PNR, but so resilience was originally introduced in engineering metallurgy as the ability of a material to resist impact without breaking. But later on used in ecology to describe the ability of an ecosystem to escape an irreversible level of degradation. It is now also very often used in psychology to describe individuals' ability to overcome a trauma. So resilience has very different meaning in different aspects. So we have to think about an ecosystem or a system which never stays the same. It's never stable. There are always some changes. So there is a natural scale, the variability, but what happens when a perturbation is stronger than normal? And then usually resilience is described with this type of graphic, what is called the basin and ball type of modeling. So we have let's say, a stability state. We have a trigger. Our system starts to oscillate, and if the perturbance is too strong, so it might reach a tipping point or the threshold, and perhaps enter a new state. Next. And for instance, as far as global warming or climate change is concerned, usually this is the type of visualization. We entered an interglacial thousands of years ago. We are warming up the planet, so it's going in this direction, the Earth's system, and if a tipping point is reached, we might enter a hot out climate. But so a tipping point can be reached and surpassed if the disturbance is very, very, very strong or of very long duration, or if the boundary conditions of the system are changed, are lower. Okay? So there are two different scenarios. The next. So we should also consider stability. Both the stability and resilience are two very important parameters in ecology. Resilience is necessary to survive irregular and unanticipated events. Stability is necessary to cope with expected normal disturbances. So the stability implies constancy. So if things remain more or less the same, okay, the ecosystem is happy, and the stability can reduce the unwanted fluctuations. But an ecosystem that is not trained to face disturbances is not very efficient. So the loss of resilience is typical of very stable systems that do not exercise their ability to counteract stress. So stability is not necessarily a good thing. The next one. Well, recently with Mariano, we made this exercise to try, and I will show to you later on, to measure the resilience of the Tethys, so this old ocean during the Cretaceous. And as I said, there is ecological resilience and engineering resilience, and they are not the same thing. So in ecological resilience, resilience is the height of the tipping point. So it's actually the resistance of the system to resist some very strong perturbation. In engineering resilience, instead, the resilience is the recovery time, overcome a disturbance, and go back to pre-perturbation conditions. So they are not the same aspect of change. So in pelagic carbonates, so these coccolith and nanolith sediments, we might have the opportunity to measure the residual resistance of this specific example group to global changes in the oceans. The Cretaceous was a very special time. Cretaceous was from 145 to 66 million years ago, so a very long time period, and it was punctuated by these black events here, which are called oceanic anoxic events. So these were times where essentially at a global scale, the oceans became deteriorated of oxygen and the sea floor, but also they were associated with very great climate change, temperature anomalies, geochemical anomalies, and excess CO2. So we can use these specific events in the geological record, try to understand the response of the oceans to this type of perturbation. Next. And in Italy, we have perhaps the best outcrops on the best section or oceanic anoxic event. So this is the example. This black interval here is about 1.5 meters in the market Apennines. So this means anoxic condition at the bottom of the seafloor, and the age of this OAE is about 90 years ago, 3 million years ago. Another for this black interval, this is older, 120 million years ago. And in general, oceanic anoxic events are natural Earth system experiments that occurred under excessive greenhouse gases and pollutants, enormous climate change, ocean fertilization, ocean acidification, and we can see the changes in biodiversity and evolutionary trends. So to put in context of higher temperature, this is one of the most recent higher temperature reconstructions. So we are now down here. And if you look at OAEs, they all occurred at times with much higher temperature, much higher temperature. By far the highest temperature of the last 350 million years were reached here. And then there was this decrease to the temperature that we know today. If you look at the paleo CO2, we are today here, 420 ppm, but back in the Cretaceous, they were probably up to 2,000 ppm in the atmosphere. The next. So we look in particular to two of these events, the late Valanginian Bisert event, 135 million years ago, and OAE 120 million years ago in the Cretaceous. And they're both related to two major tectonic igneous events that we call in geology large igneous provinces. And in this case, the southern Atlantic was starting to open up here, so there was a lot of volcanism, flood basalts, and so on. In this case, there was the construction of this gigantic submarine plateau here in the Java Plateau in the middle of the Pacific. So there are two different contexts, but they have many features together, and especially a lot of CO2 in the atmosphere or in the ocean atmosphere system. If you look at the Permian, which means our part of the world record, actually we have a lot of white limestone made of calcareous nanofossils, the Maiolica limestone. And this is the interval of the Bisert event. The Bisert event is this chemostratigraphic anomaly of the delta C13, and it has been constrained stratigraphically using magnetostratigraphy, biostratigraphy, and chemostratigraphy. So it was recognized in deep water, shallow water environment, in continental environment, on organic carbon, on inorganic carbon. So it's an anomaly that globally impacted all the potential environments. So you don't see actually much anoxia, no real black shade, a big black shade interval, but if you go at the outcrop, here, this is the first time in the Cretaceous where you have some few centimeter black shade and black chert. Black chert was not present before. So there was some anoxia, at least at the oceanic side. The next. So to make a very simple synthesis, what happened during this event? There was a major decrease of this specific group of calcareous nanoplankton, the nanoponids, so a drop in abundance, but also some species related to higher fertility in the oceans became relatively abundant, and the change in climate has been traced both with geochemistry, this warming here, but also with calcareous nanofossils, because this is one of the very few species which is living also today and they become abundant when the surface water salinity is lower. And therefore, this means this peak in abundance means a higher runoff, so river inputs of course, the pressure water. So there was a climate change, an increase in fertility, but a major decrease in bacterial monophosphate altogether. The next. If we go to the early Asia, 120 million years ago, this time the Java Plateau or the Greater Java Plateau was the super plume volcano, an enormous basalt province down here in the middle of the Pacific Ocean, which introduced up to probably 2,000 ppm of CO2. The next. This is well visible because you had white limestone before, and then when this largeness province started to be constructed, you have black shale. So it's a drastic change even from a macroscopic point of view, from white limestone to black shales. But if we look at the nanofossils, well, just look at this graph up here. This is the abundance of calcareous nanofossils and the abundance of the fluxes, so the total calcite produced by polyp pores. And it's clear that there was a first decrease here, and this was recognized everywhere, in the Pacific Ocean, in the Atlantic Ocean, in the Tethys Ocean, everywhere. So a first decline here and a crisis almost down to zero at the beginning of this OAE wave. But again, we have this peak of pentary, so the runoff indicator, climate change, and also an increase of some cockuli, which were more sensitive to higher fertility in the ocean. Next. In this case, there are also two other very interesting changes in some species. These species, Bismuth constans, that Pasquale knows, or other interval. So there were, again, in different parts of the world, definitely, let's say, a dwarfing. So the cockuli became exactly the same, but much, much smaller. And then they returned back to the normal size. But also, this is which is the most abundant cockuli in the Cretaceous Ocean. You see the difference. These are normal, and these are in the same sample. At least 30% of the assemblage is dominated by smaller, asymmetric, and sometimes incomplete cockuli. So this is not dissolution, but this is, in my view, malformation. And together, the decreasing carbon production, dwarfism, and malformation today are signs of ocean acidification. Next. So, just a summary, this is the beginning of this major climate change and a major oceanic ecosystem change, a peak in warming up, and a peak in fertilization, a major decrease in carbon production, almost down to zero. The next. The Chisholm coral that was drilled many years ago is one of the best records, full continuous record. And here you have the scale. So these are meters, so 10 centimeter, 10 centimeter, so very, very detailed. And so you start with early acidification at this level with the monochronic crisis. And then you have a further bioacidification crisis together with the decreasing activity. And only later on you start with anoxia. And just to give you an idea, from here to here there are 10,000 years, okay, with the time resolution that we can get back in the Cretaceous. And then at this level, you start to have dwarfism and malformation. So you can really separate the different steps in adaptation of populated groups. The next. So as I said with Mariano, we tried to compare the shallow water algae to the pelagic algae and trying to assess the reaction of planktonic and benthic calcifier to these two major events in the mutation. The next. So this is easy, but so we have a stratigraphic framework, again, based on magnetostratigraphy, biostratigraphy, chemostratigraphy. So we know exactly how to plot our data. This is the biodiversity for calcareous nanofossils. And so there is essentially an increase, some extinction, but nothing special, new species coming in, stable diversity, and then an origination phase upward. So this is older, this is younger. If we look at the shallow water algae, the pattern is completely different. So they did suffer of the environmental changes, and there is a major decrease in the number of species. They came back, and then another crisis. So the two calcifiers were reacting in a totally different way. Essentially, populatophores were not affected by the global change. On this side, we tried to calculate the amount of parasite production. So this is based on nanofossils. This is based on shallow water carbonates. And here, the differences are less pronounced, although there are still differences. The main difference is that this is very asymmetric. This fall in production for shallow water algae, as well as here. For calcareous nanofossils, there is a decrease and increase, which is very symmetric in the Balaginia. And here is asymmetric. And after this fertilization, they never came back to the same amount as before. Okay. The next. So just to give you an idea, this is a coposphere of the dominant populated species, Planktoninia bandese. Okay. So this is a piece of limestone. Just take a piece of rock, you put under the microscope for the early mutation, this is what you see. This was the nanoclonic words. So these are the narrow canal nanoclonics. This blue thing here. And these were the white canal nanoclonics. So this is the genetic side. There is a canal in the middle which was filled in later on during diagenesis. So, but originally this was empty. So in the next graphic, you will see this type of proportion between the narrow canal, the white canal, and the other copolypats. Okay, so the proportion of the three major components. And so we can see that as far as ecological resilience is concerned, for the Weissert event, the system was perturbed. You see, let's say the ball became smaller. There was a global reduction in total amount of populatophores and calcite, but the proportion really didn't change. So the proportion of the blue, the green, and the black. After the Paranite tendical leap here in the opening of the South Atlantic was over, or the main phase, they returned back to pre-perturbation conditions. So a tipping point was not reached. None of these three different components reached a tipping point. But if we look at the Axian 120 million years ago, at least three different tipping points were reached and surpassed. So if this is the pre-made initial perturbation, so this was the proportion dominated by the blue, the narrow canal and the column, they were almost immediately pushed over this tipping point. And you see that, well, let's say the green became less dominant, or the green became more dominant, so as abundant as the blue one, and a little bit of increase of the black cocoa. Okay. But then there was the main phase of the Great Java event, and another tipping point was surpassed. So there was a major shrink in the global population and the production of outside, and the proportion was not very different from year to year. But then when the largest province finished the major volcanic event, somehow that was a new environmental stress. So because the system went back very rapidly to a sort of normal climate or normal ocean, and that was another tipping point. So there was an increase in carbon production, abundance of property force, but the proportion became totally different from the early days. So if we go to the engineering resilience, as I said, it is the recovery time. It's the resistance, but it's the recovery time. So try to remember these fluctuations in carbon production for polygon. The next. The Weissert event. So we have a stepped decrease followed by a stepped recovery in a very symmetric way. So they could pass this major perturbation. There was not a mass extinction or even extinctions. So the white canal monophonics and the population did not suffer zero changes, but only the narrow canal monophonics, these ones, they were much reduced in number and acidification. So the resilience, which is the recovery time to go back to this type of production, was plus or minus something 3 million years, which was more or less the duration of this largest province construction. But if we go to the Ontonjava plateau, and here you have the 3 different components, there was immediately a very drastic reduction of the narrow canal components, so a tipping point was reached. And then there was a second tipping point that was reached by the white canal monophonics. And then there was a return to, let's say, stable conditions, but populated force never recovered the same proportion as before for the 3 different things. So we have some estimates of paleo CO2. So we could calculate that there was, so the narrow canal monophonics were the most sensitive and the less resilient, and they got in trouble when there was 2 to 3 times the CO2 relative to perturbation time. The white canal monophonics were suffering when 3 to 6 times CO2 was reached, concentration was reached in the ocean atmosphere system, but the other populates were not affected even when CO2 was up to 6 times of CO2 relative to perturbation. Excuse me, go back for just a second. So because the resilience is the recovery time, actually, we need to say that there was no resilience in the sense that populated force never returned to perturbation time as far as calcification is concerned, but this level is similar to this level, and from this point to this point, you have 2 million years. So it took 2 million years to go back to a 3 hardest perturbation time. Next. So by comparing these two different but similar perturbations during the Cretaceous, we could try to estimate the magnitude and duration of the stress. And this comes from very different geological data, of course, about the organism, the rate of amount of CO2 and other volatiles and so on. And as far as calcareous plankton are concerned, we can say that they were extremely resilient as a whole. So coconut, of course, did not suffer. But if we look specifically at some groups, they were not all resilient in the same way. So we can start to separate the resilience, the resistance, and the recovery time for individual groups. So coconut, of course, experience every time one of these major perturbations, I think mainly triggered by very high CO2, in combination with higher fertility, biocalcification crisis, they overcame tipping points and were able to adapt to new states. So just have a look at the evolution of leucolygophore during the Mesozoic. This is the global population of number of species since the Triassic time. And so you can see, well, a general increase up to the Cretaceous time machine boundary. That was a major crisis for extinction, but then they recovered. Actually, today they are not as diversified as back in the Cretaceous, but okay. But so you can see there are, let's say, maximum, the increase, and maximum, and increase. But if we look at the very the behavior of origination and extinctions through the Mesozoic, this is a history of life strategies, resilience and resistance, stability versus instability. So the different leucolygophore species can be separated into winners and losers. Some species could not survive even very, very little perturbances. Others could overcome any type of disturbances as well. I tried to dig a little bit more about this. If you are curious, we can talk later on. But I'm going to show you a few examples down in the early Jurassic. So starting in the late Pleistocene down here, this was one of the most spectacular origination events in leucolygophore evolutionary history. And here there is one of these huge oceanic events, a major perturbation in geochemistry, in climate, and so on. But you have one new species after the other coming out, and no extinction. There isn't a single extinction of leucolygophores during this time. So there was the beginning was before the anoxic event itself, is this anomaly here, but this did not affect, did not stop the origination phase. Another spectacular phase was close to the Jurassic Cretaceous boundary in the latest Jurassic. Again, this was a very happy time for calcifier, at least in the pelagic realm. And again, here you have one after the other, tens of new species, populates and nanno-stories appearing with no extinctions at all. And the Aptian, where we have this major perturbation linked to the Java plateau. This is the decrease of nanofossil calcite production. So you can see the various steps and the nanochronic crisis interval. But as far as evolution is concerned, you have again an origination phase with no extinction. Not a single species became extinct in this interval. So in my view, times of origination took place, or at least started definitely when the oceans were extremely stable, which is not surprising because coprolicophores are the case studies for. So they are very happy if the oceans were stable, stratified, oligotrophic, and so on. But even under a lot of CO2, higher nutrients and so on, they were not really suffering. So that maybe slowed down the origination, but were not really damaged as far as extinctions are concerned. And so at least the OAEs, this type of major perturbation did not interfere with origination and certainly did not cause extinction. We have biases, of course, that we have to face. And first of all, we look at fossils, nanofossils, so fossil coprolite and nanoliths, with very few exceptions. One or two genera, they are not living today. We try to understand what coprolicophores are doing today to understand the geological record. We still have some problem with taxonomy because, for instance, if you want to quantify diversity, so originations, new species, or extinctions, we do not use the same taxonomic approach. And so there are colleagues of mine that they split 5 species out of 1 species. And so you cannot really compare the databases one to the other, okay? There are limited complete records as far as the oceans are concerned. And we do have, at least in some part of the Mesozoic, an issue with chronology. You really need high resolution chronology today and correlate the different parts of the world. And I think one of the major bias we have is that most records are from coastal regions. They are not really oceanic. So in Italy, we have this beautiful pelagic section that was deposited in the Tagus Ocean. It was a real ocean. The Atlantic was not an ocean in that interpretation. Okay, it was like if you want the Mediterranean today relative to the Atlantic Ocean. So the big ocean was always the Pacific Ocean and partly the Indian Ocean. The next. And this is amazing because if you look at the age of the seafloor today, so there is a lot of Cretaceous. So the green is Cretaceous, the blue is Jurassic. There is a lot of seafloor out there where we, in principle, could have beautiful records of the Jurassic and the Cretaceous oceans. But, okay, just to give you an idea of the number of sites that have been drilled in 55 years of ocean drilling, starting with the FDP back in 1968 to today. So we have drilled 1,500 holes all over the oceans. But if you look at the Cretaceous in this 120 million years ago reconstruction, these are the sites, the only sites where some Cretaceous was recovered. So we know almost nothing of the real, I mean, we have no records, basically, of the real ocean. We have a lot of land section here, of course, but we don't have much in situ. And I went back and took out from my archive this figure here, and I think we still are facing some major challenge in Mesozoic paleoceanography, because if we really want to understand the ocean, the real oceanic system, we have to go to the normal oceanic system. out there in the Pacific, which was the only real ocean back in the Cretaceous and Jurassic. So one challenge would be to drill what they call TOIS. This is ocean sinking. And the ocean's oceanic crust might be in the Ionian Plain, very close to us, okay? So it seems that we might find there the Triassic oceanic crust. If the geodynamic reconstructions are correct, okay, so by far the oldest Jurassic crust and sedimentary sinking. But we need the Japanese ship to do this. So there are technical issues because we should go down into the Ionian Basin and drill for some 7 kilometers before reaching the supposed Triassic crust. And at the moment, this is not possible. And another stupid but important issue is that the CQ should take, I don't know how many months to come from Japan into the Mediterranean. It's a lot of money to have the ship just traveling, entering the Mediterranean and drill a hole there. But who knows? The next challenge is the Somali basin. There is an ODP site, a DSDP site drilled here. We know the Cretaceous is there. We know it is pelagic in character, but the recovery was awful. And it's also a very thick sequence. So again, the only way to go here is to take the CQ, the Japanese ship, and go there. Here we have an additional problem, which might be, let's say, folkloristic, but it's real. There are pirates here. So the ship will not go there and drill. So sometimes science has to face a very unusual, issue. That's life. But if we want to understand the evolution of the Indian Ocean, and this part of the Indian Ocean, you have to go there and drill there. But, so after decades of research, we know a lot about the Mesozoic oceanic system. And so we know a lot about the extreme environments, the extreme perturbation. And I think that on the other hand, we know very little, almost nothing about the normal ocean, the unstressed ocean. We all focus on these amazing experiments of high CO2, high temperature, high acidification, but it's an exception relative to what? Which was the normal Cretaceous ocean? We know very little. And so actually we have no real idea about the concentration of atmospheric CO2. We have many different proxies, so maybe up to 2000 ppm, but who knows for real. We know very little about the normal variability in ocean chemistry, fertility, and temperature, and therefore the normal variability of the oceanic ecosystem. And the answer is written in the boring pelagic sediments. This snowfall going down slowly to the sea. But there is one place that was already drilled back in the early days of the SDP. Here, Magellan Rise was this plateau here. This formed in the late Jurassic time. Okay? And you have to imagine like a very special place in the middle of the Pacific here. And so it was definitely shallower than the CCD. And this place collected the snowfall of coccolithopores going down to the sea. So because it was not affected by the solution of the CCD. So this was already drilled, site 176. Again, the recovery is awful, but all these anomalies are there. It went down to the Tissonian. Logging was not even a concept in the early days of the SDP. It was already there, so we know it's doable. We know that there are no real risks, but logistically, it's in the middle of the Pacific Ocean. And if you don't have a stronger lobby of scientists that want to go back in the middle of the Pacific and drill again, it will never be drilled again. But that's a place where we have already an idea of the expectation. So, higher latitude, because the Pacific plate is moving. So today, Magellan Rise is up here. And okay, we can calculate the higher position. And in the Jurassic or in the late Jurassic, Magellan Rise was here. And this is perfect if you want to study the quiet Pacific Ocean, because it was not well insisted. And there is a lot of cognitive force that were living and were collected at this site. So, my hope is that the next generation will take over. There is a lot of things to be understood and to be characterized. And the oceanic record is really essential to understand our present and our future. Thank you.
We have time for questions. First from the audience here in the room, then we go online. Don't be shy. Pasquale, please.
Yes, thank you for truly amazing, truly amazing. Two questions. Actually, I don't see the sheet very well, but just regarding the very last slide. Of course, as you know, I do mainly focus on terrestrial ecosystems in the future. We basically use a global situation notebooks to understand what's going on in the future. What do we expect? And the worst case scenario is one of those one you have used. I try to recollect cues to understand, kind of trying to design a prediction for what is in front of us. And I see a very big difference that for me at the moment is a very big hurdle that I cannot overcome. Asking for your help. There is a very big difference now. And the point is that there is a huge amount of fresh water that is expected to go into the ocean because of the glaciers that are melting, especially the Arctic, and hopefully not in the south, which makes it different from what we have said so far. I cannot imagine all the potential feedback because with so much fresh water going, we do expect a change in pH, of course, and even less acidification. But the point is that after the very first moments, we do expect more acidification as expected in the atmosphere. So my question is very simple. A student like one, what do you expect, given this huge difference? I mean, the melting glaciers as compared to what I can use.
It's a scenario which is totally different. Because, well, in the basic glaciers, there was essentially no ice, no permanent ice, nowhere on the planet. So we had really on the other side, extreme side of situation. Although, for instance, during the Valanginian, I don't know if you want to go back, but there was an initial warming globally, but then it was quite surprising that the end of the Valanginian So if you look at the temperature change, and this is based on very different geochemical processes. So there was a warming associating, these are radiometric phases, on the left-hand side, so CO2 equals 1. But there was a major cooling, so the end of the Bicep event is marked by cooling with evidence of dropstone, glandonites, both in the north and the southern hemisphere. So some ice was forming on Antarctica and perhaps also in the Arctic region. Okay. And then there was an interruption and then the second cooling. And what comes out is that at high latitude, in that interval, the gray between the two blue, so there was a warming or a relative warming, and you have all these pentalic only at high latitude. So indeed, that might be evidence of melting of ice at high latitudes that was introducing fresh water, called the fresh water, into the ocean. And so if you're asking about the coccolithophores, nothing really changed. Again, as a whole, they could easily survive in a type of climate change or age and so on. But you have some specific groups that they were, getting advantage, if you want, or disadvantage of this. So the main difference is that we have no idea. We have no idea in the Mesozoic about melting of ice at high latitude because there was no ice for the ice. There are many changes that are occurring today in the oceans, like deoxygenation already going on. If we look at the changes, they are exactly the same as for oceanic anorexia. Timing is very different. So back in the Mesozoic, everything was at much slower rates. So perhaps biota had enough time to get adjusted and survive. I'm not sure about the speed that we are imprinting today if the biota will be as able as back in the Mesozoic to react or to survive or take advantage. So I'm not very helpful, but generally speaking, I think the problem with the Mesozoic, Maria, maybe you have some more comments on this, but we really have very few pelagic, oceanic. So we have a lot of data from the Atlantic, but the Atlantic was not a real ocean, so cannot be the example for our future. And then we have a lot of sections piled up in the Himalayas, Karakoram, but tectonics was so intense that you cannot recover much from that part of the world.
Yes, but the very few news that I get from the talk and from your response are all bad news. It seems to be the same, but it contains in a very short time, just three orders a month, which is fast.
Yes.
Bad news for us are good news because we are scientists, so problems are workflows.
David. I was curious looking at your slide. Going back to the bad place, which is the Atlantic Ocean at the time of 120 million years. One of the big problems for people who look at the deposition of the initial deposition of the salt in all the Brazilian side, there is a lot of fight about what is the real age of the salt. My question is, I never see, I just be frank, I never read with details all the paper which are taken and using all the information, using the various proxies, etc. But is that across all the basin in Brazil, is it impossible to use the coccolithophoric basically information out of that? Because I've never seen paper about that. Using it.
Essentially the first continental to very shallow marine and turbidity.
So the shallow marine, but because there are some couple of basins, which at least if you read some of the paper, which the idea that the oceanization in the Brazil has been very diachronious and also with different velocities. So probably in some place you may have deeper around this 120 million years, deeper pelagic basically event, while some others where all the people are looking, which are the Santos Campos basin, in reality much. But you have to use the acoustic.
Because the Atlantic, the South Atlantic was opening this way. In the southernmost part of the South Atlantic, yes, you have nanofossils that you can date. Okay. But so the oldest site, I mean, the site with the oldest nanofossils, as far as I know, it's up here. It's site 364. Okay. And also you have the Portland on the other side, but that's higher latitude. So there you have the lower. So as far as I know, the oldest, let's say up here, okay, the oldest nanofossils, the early Cretaceous here are Albion, I would say. Not because it was closed before, but it was too shallow or too extreme as an environment. But there are a couple of papers. Well, chemostratigraphy is potentially useful. It might be some late option, but not with nanofossils. If you use chemostratigraphy, you might have some marine sediments that is post-OAU1A. But nanofossils no older than Albion function.
Thank you.
Any other questions from the audience? Roberto.
I appreciate very much your work, but I hope the progress. Our opinions. We have link between triggering mechanisms and consequences. I mean, we have to work in cause and effect relationships. And when we do not have very high resolution stratigraphic record about triggering mechanisms, maybe organisms or whatever impacts and biotic and sedimentary management species. But we have a lot of problems. For example, we still rely on certain African, still rely on the fish canyon setting. The last few years, we had videos published about the M0 the absolute age, the chronology, and so on. And if you take into considerations the consequences, sometimes comes before the imputed the proposed triggering mechanisms. So this is a type of a methodological question I make you. Which would be, in your opinion, the best tool for addressing this discrepancy, about causes, imputed causes, and consequences?
This is still a major problem because in dating sedimentary section, we use chronostratigraphy, which means biostratigraphy, stratigraphy, chemostratigraphy. So the framework and the sequence of changes are extremely well constructed in the system. And then we have the numbers, graduated ages. And these are two independent tools totally independent. There isn't a single section in the world with chronostratigraphy and a datable volcanic layer for the Aptian or for the Valentinian, for instance. And so this paper about the zero, well, they have a reversal somewhere, and they have a number which is close to the base of the Aptian, but that depends on the time scale. I'm sure all the geologists are familiar with time scale. Take the last 5 time scale. Okay.
Yeah, then it's one
Okay, so Aptian goes from 120, 124, 121, 126, 125, and so on. And so for very different reasons. And so when we made an exercise a few years ago, just use 2 different time scales. The actually found that was high value about 2012. So the same year, totally different time scale based on different methodology. Okay. So, well, I can tell you which is which, but if you take one time scale with the numbers, then the open Java, or the great open Java, comes before all these environmental changes. If you take the other time scale, you have a lot of catastrophic changes in the oceans with no apparent cause. And then you have the quiet after the storm, and you have the autumn Java plateau eruption. And well, this is not evidence that the second time scale cannot be correct, but I mean, but you have to be careful. The same is for the Valentinian. Originally, from the very beginning, it was thought that the cause of the Valentinian is the Fahrenheit and the Fahrenheit problem. At that time, the radiometric ages and the time scale were nice to put the cause and consequences. And then they started to change the numbers for the rotation. And so then again, we had a problem because there was a mismatch of 2 or 3 million years between the cause and the consequences. Now we are back to more or less the same radiometric age as the current last age. The problem with the qualification or qualifications in the Western Interior Basin, there are tens of volcanic layers interbedded with ammonites and nanofossil planktonic forms. And so we have radiometric ages and biostratigraphy, chemostratigraphy, and so on. So the Cenomanian-Turonian boundary is more or less fixed, 93.5. Although you have 4 different volcanic layers with 4 different numbers, but okay, the average is 93.5. Okay. And then we know where is the next volcanic layer that is interbedded with biostratigraphy, magnetostratigraphy, chemostratigraphy. You know where? In which time interval?
With the Jurassic.
153 million years ago in your scorpion. So all the rest is extrapolating. And so you can have a perfect match, very different numbers. On the other hand, now there are a lot of provinces coming out all over the world. So you can have any for any environmental change. But this is a problem unless we find a workable, a layer which can be given interbedded with integrated stratigraphy, we will always have a problem. As far as I know, even for the same point, where the astronomical time scale has been constructed, the ages derived from the melancholy cycles do not match with the rhythmic ages. So, yes. And so, I mean, we have to find, because this paper I got in here, they made our best, but the correlation are awful.
Yeah.
So,
It's much for physicians to construct more sensible instruments for deriving better radiometric ages probably.
or because we are others,
Quindi vedi, è giusto.
intergalactic geology will be stratigrapher should go back to the field and look again. There are probably some volcanic areas in the valley that over time.
You must use books
Yes,
going to mountains again.
yes.
Absolutely. Sure.
Well, in a way, mercury isotopes can link the volcans to the sedimentary section, even if you don't get any datation, but you know where there is the peak volcans. Some instances.
And also.
Okay. Any other question from the audience or from the few people that are still surviving online? If not, I have a comment. So it's a letter showing several sites really in the ocean. She's the real expert. She's the president of the Olympic Italia committee. So she has been always there for a long time. She started her career involved in deep sea drilling. And she came here to Naples to give this presentation, but also because she's in charge to organize the outreach activities that will go on when the joint resolution will arrive in Naples. You will probably know, or if you don't know, please be aware that the joint resolution will be here in Naples in February, next February, and then again in April, because there is an expedition in the Mediterranean after so many years. So you will have the opportunity of visiting the joyous resolution and visiting some exhibit that will be organized in different places, even here in this department, and the museum, in the historical town, and the art. And so please stay tuned, because it's a great chance of looking at one of the biggest enterprises in Earth sciences, that is ocean drilling. It's something that really has shaped our knowledge about the planet. And we still miss a lot of evidence, but the joyous resolution did a lot of work, and it's about to be retired. I mean, she will retire. The ship will be retired, and it's the end of an era. So if
Ma la cosa bellissima sarebbe, no? Che ci salissero degli scienziati italiani che si dall'Italia. Quello sarebbe bello. Quello perché quindi ci stanno un paio di imbarcati, ma qui sono non so, non mi ricordo niente. Quando gli italiani sono nazionalisti.
please speak English. But anyway, wherever time.
First one was
Okay. So we have no other question. We thank again Isabella for this beautiful. Attending the conference. We will have a break now in the series of initial lectures. Actually, the next one will be next year, in January. So you will receive my message. Okay. Thanks a lot. Thanks a lot. Okay.